We're going to continue our study in trig equations today. In particular, we're going to talk about what happens when you're working with a trig equation and it's not a value that's on the unit circle that we can easily find. What do we do in those cases? And then we're going to also look at some cases where you might have a trig equation in there, but you might also have the variable outside of it. And we'll also look at some cases where you might have a combination of functions, not just a trig function, but another type of function in the same equation. So let's start with what happens when you have a solution, but it's a solution that is not a memorized value. So we use inverse functions to solve trig equations when you know a solution exists, but they are not on your list of memorized values. So for example, we know a solution will exist if let's say we have sine of x is equal to a value between -1 and 1, so we know a solution does exist. But let's say sine of x is equal to 1/5. In that case, we know there's a solution, but we don't have a memorized value for when sine of x is equal to 1/5. We have it for 1/2, we have it for 2/2, 3/2, but we don't have it for 1/5. So just for example, sine of x is equal to 5. We know for a fact that that does not exist because that's greater than 1. But on the other hand, sine of x equals 1/5. Well, that's going to be sine inverse of 1/5. So we will use an inverse function to solve these types of equations. Take a look at example 1. Secant squared of x minus 2 tangent of x is equal to 4. We have two different trig functions in their secant and tangent, so we're going to want to make sure that we get everything just in terms of one of the trig functions. So in this case, secant squared, we can replace that using a Pythagorean identity, and that would become tangent squared of x plus 1. So if we replace that, we end up with this right here. And then let's move everything over to one side and combine like terms. So we'll have tangent squared of x minus 2 tangent of x minus 3 equals 0. Now this looks like a quadratic that we might be able to solve. So if you want to think of it as x squared minus 2x minus 3 equals 0, and then factor it, you can. So we'll end up with tangent of x minus 3 and tangent of x plus 1 as our two factors equals 0. Set each factor equal to 0. So we have tangent of x minus 3 equals 0. Tangent of x plus 1 equals 0. Now tangent of x for the first one would equal positive 3. Now remember, tangent does not have restrictions on the range. Sine and cosine have to be between 1 and -1, but not for tangent. So we know this is going to have a solution, but we don't have a memorized value for when tangent of x equals 3. So we're going to have to deal with that. So use the inverse trig function. So tangent inverse of 3 is going to give you x. And then remember, for tangent, if you're asked to find all solutions, that's plus or minus k times pi. Now, you absolutely can put this into the calculator. Make sure you're in radian mode because we are giving our answers in radians here, especially if you're going to tack on that plus or minus k pi. But do note that when you are putting it into the calculator, it's only going to give you one of the solutions. Now, you know that tan inverse of 3 is going to have two solutions within 0 to 2 pi, right? Because tangent is positive in quadrant 1, and it's also positive in quadrant 3. Now the calculator is only going to give you the radian measure in quadrant 1. So just be aware of that. You are absolutely free to write in tan inverse of 3 into the calculator, but just know it's only giving you one solution. It's really just giving you the reference angle. So if you do find that measure, you're going to also have to add pi to it in order to find the solution that's in quadrant 3. Now you can also just opt to leave it as tan inverse of 3 plus or minus k times pi. That's absolutely fine with me. Now for the second one, we have tangent of x equals -1 if we subtract 1 from both sides. And where is this going to be -1? Well, in two different quadrants, tangent is negative in quadrant 2 and in quadrant 4. Now, 1 is a memorized value, right? The reference angle is pi over 4. So in this case, in quadrant 2, our angle is 3 pi over 4, and then it's plus or minus k pi. And then in quadrant 4, that would be 7 pi over 4 plus or minus k pi. So those are all your solutions for this example. Let's take a look at example 2. Find all solutions for 5 sine squared of x minus 2 sine of x equals cosine squared of x. So first things first, let's get everything in terms of just one trig function. Now I think for this one it would be easier if we changed everything to sine. That way we only have to change the cosine squared. So cosine squared, using a Pythagorean identity, would be 1 minus sine squared. And now let's try to move everything over to one side and combine like terms. So add the sine squared over to the left. That gives us 6 sine squared of x minus 2 sine of x, and then we subtract the 1 over as well. And now we can write that as 6x squared minus 2x minus 1 equals 0, if that's helpful, and see if we can factor it. Okay, now for this, it's not factorable. So what do you do when it's not factorable and you're working with a quadratic? Here's where we're going to have to apply the quadratic formula. So sine of x is equal to 2 plus or minus negative 2 squared minus 4 times 6 times negative 1 all over 2 times 6. Okay, inside the square root there we have 4 plus 24, so that's the square root of 28. Now, we know that there's a solution here. How do we know? Well, because 2 plus square root of 28 divided by 12, if you were to plug that into the calculator, would be a value between 1 and negative 1, and same with 2 minus the square root of 28 all over 12. Alright, so that would give us sine of x equals 0.6076, and sine of x equals negative 0.2743. And then to solve for x, because we are working with values that are not memorized values, we are going to use the inverse function. So x equals sine inverse of 0.6076 plus or minus 2k pi. And same thing with the other. X equals sine inverse of negative 0.2743 plus or minus 2k pi. Let's look at example 3. This one says, find all solutions for x equals 2 times sine of x. Now here's an example that's different from the other examples we've seen so far. In this one, we have x by itself on the left there, and then on the right we have x as part of the function, the trig function, sine of x. If you see something like this, the way that we're going to go about solving this is by graphing. So how do we solve by graphing? We're going to first move everything over to one side. So we have x minus 2 times sine of x equals 0. And then we're going to solve this by plugging this in and trying to find where y is equal to 0. Well, that would be where the x-intercepts are. So in the calculator, you'll put in y equals x minus 2 times sine of x. You want to make sure you're in radian mode when you go about graphing these. And when you hit graph, you should get a graph that looks something like this. Now, if you were to zoom in really close, or a lot closer, you'd be able to see a lot better and more clearly that there are 3 places where it crosses the x-axis. Those are the 3 that we want to find. So just as a reminder of how to do this on the calculator. So on the graphing calculator, once you have it graphed, and you want to find the zeros of this function. So you're going to hit second, and then the trace button, that's going to be calculate, and you want to calculate the 0. Hit enter, and now the calculator is going to ask you for a left boundary and then a right boundary. So what you want to tell it is find me the 0 that's between here and here. So if we start with the one on the far left, we're going to go ahead and move this all the way until we've passed that 0 for sure. So something like this, definitely past that first intersection there. I hit enter, and then it asks for a right boundary, so I'm going to now move this as far to the right as long as it has passed. We don't want to go too far, otherwise we might have multiple zeros in there. So just far enough so that you know you've passed the 0. Hit enter, and that leaves us with, enter one more time, the 0 is at negative 1.895. Now you can do the same thing for the other 2 zeros. You hit second, trace, 0, give it a left boundary, hit enter, give it a right boundary, hit enter, and it will give you the zeros. You just want to make sure that what you're doing when you're giving the left and right boundaries is you're telling the calculator, find me the 0 between here and here. So you want to make sure you only have 1 0 between those two boundaries. You should end up finding that the other zeros are at x equals 0 and x equals 1.8955. Okay, let's do an example where we have combinations of functions. But before we do that, what do I mean by that? So some trig equations might involve other functions within the equation. So not just trig functions in there, but you could also have any other function that we've talked about before, like say a square root function, or a log function, or an exponential function. So in example 4 says, find all solutions. Tangent of ln of x minus 1 equals 0. Okay, so notice how in this case we have another function in there, ln of x, but notice how that's inside of the trig function. So since it's inside the trig function, let's still try to isolate the trig function on its own first. So tangent of ln of x is equal to 1. Now let's think about what value has to go inside of the tangent function in order for it to equal 1. Well, it's a positive 1. So first we know that the reference angle we're using is going to be pi over 4. We also know that tangent is positive in quadrant 1 and in quadrant 3. So whatever's inside of the tangent function, which in this case is ln of x, has to equal pi over 4 plus or minus k pi, because it's all solutions, and ln of x is equal to 5 pi over 4 plus or minus k times pi. Okay, so now the last thing we need to do is we need to somehow get x by itself. Now we've successfully taken care of the trig portion of the solution, but we haven't taken care of the log function, right? So in order for us to be able to get x by itself, we can use the exponential, apply it to both sides, and in this case, since we're working with natural log, we'll want to use e as our base. So if we raise e to the ln of x, it'll equal e to the pi over 4 plus or minus k times pi. Same with the other one. E to the ln of x is equal to e to the 5 pi over 4 plus or minus k times pi. And we know that e to the ln of x is equal to x. So that leaves us with x equals e to the pi over 4 plus or minus k times pi. And x equals e to the 5 pi over 4 plus or minus k times pi. Okay, the last example we have e to the x times sine of x minus e to the x equals 0. In this case, this is different from the last example because the two functions are not, one isn't inside of the other. However, they're still in the same equation, but in this case, we have e to the x times sine of x minus e to the x. So what we can do here is we can actually factor out the e to the x. So e to the x, parentheses, sine of x minus 1 equals 0. Once we have it factored out, we can just set each factor equal to 0. So e to the x equals 0, and sine of x minus 1 equals 0. And then we'll solve each of these. So for the first one, if we were to solve for x, we would take ln of both sides. And that way we can move the x out in front. Ln of e is equal to 1, so x is equal to ln of 0. Now what is log of 0 equal to? Well, if you recall, we can't take the log of 0 or of any negative value. It has to be log of a positive number. So in this case, there is no solution. For the second part, sine of x minus 1 equals 0. We have sine of x is equal to positive 1. Thinking about the unit circle, where is the y-coordinate equal to 1? At the top of the unit circle, which is when x is equal to pi over 2. So x equals pi over 2 plus or minus 2k pi. And that's the only part that we actually have a solution for.